Guangzhou Valley in China. At 1,854 feet below the ground, this massive crack in the earth has separated the local community for centuries. New York-based architect Wendy Falk has traveled to this remote region to see how extraordinary engineering is pushing the boundaries of what's possible.
Canyons are pretty dramatic. It's beautiful around here.
She's attempting the dangerous journey across the valley.
It's kind of crazy ride. Roads are really bumpy, and the only way to get from one side of the county to the other is through this road. It's very frustrating because it's a 5-hour drive.
The long trip down the steep slope and up the other side is treacherous.
It's dangerous, the road, because there's a lot of sharp rocks, lots of steep gorges. You also see a few landslides, so piles of rocks on the side of the road, so drivers have to be very careful.
This natural divide has a devastating effect on the community.
There's 35.8 million people in this region of Guangzhou. With all these windy roads and steep valleys, it's very difficult for the local farmers to get the goods out of this county to sell them. So as you can imagine, it is one of the poorest regions in China.
A solution is desperately needed. But with a nearly half-mile drop to the valley floor, nobody has ever bridged a gorge this deep. The solution engineers in China have come up with is breathtaking. This is the Beipanjiang First Bridge. With a deck nearly 2,000 feet above ground, it's the highest bridge in the world.
It is remarkable how high this bridge is and how long it extends.
And at almost a mile long, it's one of the longest cable-stayed bridges on the planet. Liu Ba is deputy chief engineer of the bridge.
So this is the Beipanjiang Bridge. Yeah.
It's normally off-limits to pedestrians, but he's giving two colleagues a unique tour.
It's very high.
Very high?
Very
yeah.
high.
When we came here, it's very difficult to go to the two sides. Yeah. It's the highest bridge in the world now. Yeah.
Such a beautiful bridge.
The bridge is made up of a pair of massive concrete towers, the tallest reaching 883 feet high. The 22,000-ton steel bridge deck is the length of 5 Titanics. It's so high, one World Trade Center in New York could fit underneath. The deck is attached to the towers with 250 miles of cables, enough to stretch from New York City to Washington, D.C. But to create this unprecedented structure, the team need to solve many tough engineering challenges. How do you construct terrifyingly high concrete towers?
It's very difficult to pump the concrete from the bottom to the top. It's really a critical issue during the construction.
How do you assemble a super long bridge deck in such a dangerous environment?
The valleys here are so deep you can't even see the bottom. This is too high to build temporary scaffolding for a bridge deck.
And what type of bridge do you build on vertical cliffs full of hidden caves and crumbling rock?
To build a bridge here is really a great challenge for me. I'm not sure we can achieve or not.
Before engineers could even get started, they would have to find a way to work with the area's deadly geology.
The rocks around this region are very soft. Also, it's very steep. To make things even more difficult, there are a lot of hidden caves and cracks along the mountain. This poses a huge challenge for the engineers to design the bridge.
Most types of long-span bridges need support anchors built into the rocks. For an arch bridge, weight pushes down, and the bridge's curved shape moves the force sideways. So they need gigantic anchors in the banks. On a suspension bridge, the deck hangs from 2 cables, which also need huge anchors to keep the bridge from collapsing. But the soft, crumbly, landslide-prone rock in this region isn't suitable to hold massive bridge anchors. Leo Ba is on site surveying the rock.
This is an example of the difficult geology, the limestone rock, and you can see so many caves and cracks on the rock. That's quite a big issue for the bridge design and construction. It's really a nightmare of the engineer.
The only option is to find a bridge design that doesn't need the support of anchors, which means the team will have to draw inspiration from the pioneers of the past.
This is amazing. A tour of London on a beautiful sunny morning on a boat on the River Thames.
Physicist Andrew Steele is exploring London from a unique perspective.
Look at this absolutely beautiful structure. It's the iconic Tower Bridge. From down here, this structure just looks absolutely enormous.
There's an incredible range of bridges in the British capital, which could help inspire the team in China.
This is Blackfriars Bridge. It's an arch bridge. It was constructed in 1869, and from underneath you can see these beautiful wrought iron ribs which are holding the whole structure up. Here we have Chelsea Bridge, a suspension bridge. You can see that big red cable running along the top. That's the main cable.
Among these famous giants, there's a lesser-known bridge that's actually one of the most important in the world.
This is a piece of engineering history, an entirely new type of bridge that people didn't think at the time could even be constructed.
Built in 1873, this is Albert Bridge.
From an engineering point of view, there is an awful lot going on here. You can see we've got these support columns, we've got the curved cables, the straight cables. Pretty daring for the time.
Albert Bridge is the brainchild of British engineer Roland Mason Ordish, who was determined to build the impossible.
The Victorians had managed to build loads of different kinds of bridges, but there was one particularly desirable design that remained elusive. It's called the cable-stayed bridge, and the idea actually dates from centuries before. It was in the 1600s that the first cable-stayed designs were proposed, even before the existence of actual cables.
The design of a cable-stayed bridge means all the weight is carried up through the cables and down through the towers, so it doesn't need anchors on the banks. But in the 19th century, building a cable-stayed bridge had never been successful because the forces are so complex.
The problem was the maths was just too hard. Imagine trying to calculate all the forces on one of these cable-stayed bridges. You've got loads of different cables, all at different angles, pulling on the bridge, pulling on each other. It's a trigonometry nightmare.
Over-tensioning even a single cable could lead to a catastrophic failure.
For 200 years, people thought the cable-stayed bridge was never going to be built.
Ordish knew the risks of building a cable-stayed bridge. So to ensure Albert Bridge didn't fail, he ingeniously combined it with a suspension bridge.
From up here, you can really see what's going on with this bridge. Since we're in the middle, this is the main cable, the suspension bridge aspect of this structure. And we've then got these smaller suspenders. And what these do is connect the main cable to the span of the bridge, allowing it to support the bridge at multiple points along its length. And then finally, this is what makes this bridge so special. Here we find the cable stays, and it's really clear from this angle what they do. They're taking some of the load from this span and then transferring the force up into those towers there. This is two bridges in one, and that is the genius of Ordish's revolutionary design.
Albert Bridge was a major step towards building a pure cable-stayed bridge that didn't need anchors. Exactly what the engineers in China are looking for. And today, cable-stayed bridges are commonplace.
So when you see a modern cable-stayed bridge, it's all thanks to pioneers like Ordish, who, over 150 years ago, showed that this elegant and deceptively complex design could be done.
In China, engineers are building on Ordish's groundbreaking work and supersizing it for the 21st century. The Guangzhou and Yunnan regions of China, separated for centuries by this cavernous abyss, until now. This is the Beipanjiang First Bridge. The bridge stretches almost a mile across the ravine. The tips of the towers reach 2,461 feet above the valley floor, higher than 2 Eiffel Towers and the Statue of Liberty combined. And it's the first ever cable stay crossing to hold the title of world's highest bridge. Architect Wendy Falk has special access to this engineering marvel.
This bridge is amazing. This is so exciting. I'm gonna actually go and climb over this and take a closer look at the cable stay myself. The view up here is absolutely insane. It's actually quite amazing that this bridge is held up by the cables and by these amazing towers that are on the left and right of us. So there are no anchors on this bridge. The only way to build this bridge in this region is to have a cable stay design.
The load from the 22,000-ton deck and everything on it is carried through 224 cables into the towers and down into the foundations, removing the need for anchors. But attaching each cable was an extensive job for engineers.
There's actually a lot of smaller cables on the inside that's bundled up that is then connected onto the anchor point on the bottom.
First, one of the cable strands is pushed through a waterproof casing. It's then attached to one of the towers and joined to the bridge deck. More strands are then threaded through the casing. Up to 43 make up one cable bundle, the longest of which is 1,253 feet. Each bundle is tightened into a carefully calculated strain.
Getting the cables and the tension right in this bridge is crucial. So inside of each of these cables is a gauge that measures the constant tension on this bridge.
If any of the strand cables fail, engineers in a control center can immediately spot and replace them.
The marvelous aspect about this bridge is that even if you were to remove one cable, the bridge is still stable. And that's pretty incredible.
But winter in Guangzhou brings a new onset of problems. It is one of the most severely frozen areas in western China. And because of the bridge's altitude, ice could form on the cables. It's a potentially deadly problem that Liu Ba and his team have to solve.
If the ice spreading comes, there will be some problems related to the safety of the traffic.
So the ice will cover the cable in the winter.
Yeah, the ice will accumulate. Most bridges propose the cables in the middle, just above the carriageway.
Yes.
When the ice accumulates, on the cables, there will be ice fragment falling down onto the deck.
With the risk of falling ice causing a potentially fatal traffic accident, engineers came up with a brilliantly simple solution.
For this bridge, we propose the cables out of the carriageway on the edge of the deck. Then ice drops out of the carriageway.
That's very clever.
Yeah.
Moving the cables to the edges of the bridge will force ice to fall safely into the valley and keep this lifeline flowing all winter long. But engineers have even greater challenges ahead.
In order to build the tower, the engineers have to think about getting concrete all the way up to the top. It's just mind-boggling.
Guangzhou Valley, China. Known as the crack in the earth. To cross it, engineers are taking on the impossible. With the world's highest bridge. The Beipanjiang First Bridge is a crucial crossing for millions. At almost a mile long, and with a staggering 2,362-foot main span, this is a cable-stayed bridge on an epic scale. But designing a structure of this magnitude presents a terrifying set of challenges. Architect Wendy Falk has traveled from New York to check out this engineering marvel.
This bridge is incredibly long, and it's really rare for a cable-stay bridge to be this long.
Devising a super-long cable-stayed bridge is extremely complex. Everything is connected. If one thing changes, everything else is affected too.
Imagine my hands are the cables, and as the span of the bridge gets longer, the angle of the cables get flatter, and that's bad because it puts the deck under compression. There's an optimal angle for these cables, which are 30 to 40 degrees. And in order to build a bridge this long, you need a very tall tower. Basically, the longer the bridge, the taller the tower.
This exceptionally long bridge needs exceptionally high towers.
In order to build the tower, the engineers have to think about getting concrete all the way up to the top. It's just mind-boggling.
So how do you build soaring concrete towers? The answer lies with a pioneering innovation from the past.
I'm pretty excited to be here. This is a really special piece of engineering history, and not many people get a chance to come here.
Physicist Susie Sheehy is in Hampshire in the south of England.
330 steps. I don't even think I'm halfway.
She's getting an exclusive look at a little-known but vital piece of engineering history.
In the 1860s and 70s, there was a huge fascination with building stuff with concrete. People would build sculptures and other objects, but no one had yet dared to build something as audacious as a tower out of concrete. They all thought it would collapse under its own weight.
But one man was determined to prove everyone wrong.
Aha! Finally made it to the top.
This is Sway Tower.
Oh, wow. What a view.
Topping out at over 200 feet. When it was built in 1885, it was the tallest concrete structure in the world.
I can see the whole forest, and I can see the sea. It's incredible. I can just see for miles in every direction, framed by these beautiful, beautiful windows. Definitely worth the climb.
Sway Tower was built by Andrew Peterson, a retired judge with a passion for architecture.
What's incredible is that all of this was built by Peterson, who was just an amateur enthusiast, and yet he made this huge impact in civil engineering.
Just like the engineers at the Beipanjiang Bridge in China, Peterson needed to build tall concrete towers. The ingenious method he came up with would change the world.
So how do you make a concrete tower? Well, obviously concrete, and a mould to form it in, and the concrete then gets pressed into the mould. The next step to build my tower up is to get another mould and keep going. That's looking pretty good, so I'm going to add a third one.
But in the 1800s, the molds were the most expensive part of building with concrete. Peterson came up with a brilliantly simple solution to use fewer molds, but still build high.
By the time I've poured in the top two moulds, the bottom one has set. So then I can remove the bottom mould and place it back on the top and keep going. And then you could just keep doing this, moving the different moulds up, and the tower would grow floor by floor. And the only limit was how tall you dared to go.
It's called climbing formwork.
Yes, there we go.
And it's still the go-to method for building tall concrete towers.
Oh goodness. There we go. I think if Peterson saw this, he'd think I need a little more practice before I build a real one.
Incredibly, Peterson used just 3 molds to build this entire concrete tower. It's still the tallest non-reinforced concrete structure in the world.
What's incredible is you can still see the lifts where each of the layers of concrete was poured, and it would have taken 2 days to fill each one and then 2 days to move the bottom one up to the next layer, and it took 6 years to build. Peterson proved the world wrong. He showed us 130 years ago that we could build a tall tower out of concrete, and that paved the way for us using concrete in structures today.
Now, engineers in China are using Peterson's revolutionary construction method and taking it to the next level. The Beipanjiang First Bridge in China boasts 2 massive towers, the tallest reaching 883 feet. Engineering megastructures in their own right.
This thing is colossal. You can see from top to bottom, it's just so big.
But before these towers could be built, engineers first had to make more than 130,000 tons of concrete. Zhou Ping, director of the Beipanjiang Bridge, is tackling this issue.
To make a bridge, we need tons of concrete. To make concrete, we need lots of sand. But you can see around here, there is no natural sand. It's a huge problem.
The answer was to use the difficult environment to their advantage.
To solve the problem, we produce millions of tons man-made sand. Just like this, we make it by crushing and grinding rocks into small pieces.
Crushing the soft rock to make sand is an ingenious idea, but it also has an added benefit.
We can control the size of the man-made sand to make different strengths of the concrete.
Finally, construction of the towers can start. Thousands of steel bars are formed into a grid to reinforce the concrete once it's poured. Just like at England's Sway Tower, climbing formwork is the key to raising these super towers.
In order to build the tower, the engineers had to design a mold. And then they added concrete into the mold and then lifted it up manually so that they went up section by section.
Assembling the molds manually enables precise control, so engineers can form the demanding H-shaped design. But as the towers grow, so do the challenges. Initially, concrete is lifted in enormous vats by huge tower cranes. But at greater heights, a pump is needed.
Man-made sand is a little bit rougher than natural sand, so it is difficult to pump up to the top of the tower. So we have to use a great pressure pump to pump it up.
A high-powered, gravity-defying pump is used to propel the thick concrete to a height of almost 900 feet.
These towers seem to be going on forever. You can't even see the top of it. It is quite amazing here.
More than 12 million gallons of concrete were used to make this pair of colossal towers.
And you can still see the lines that are left behind from the mold all the way to the top, and that's pretty cool.
These exceptionally tall towers ensure the cables are at the optimum angle to take the weight of the massive bridge deck.
Because the bridge needs to be so long, these towers need to be so high, and the engineers definitely did that.
But to bridge this mighty chasm, engineers will face their greatest obstacle yet.
It's impossible to build a scaffolding to reach up here.
Guangzhou, the most poverty-stricken region in China. This impassable valley restricts development. The solution? The Beipanjiang First Bridge, the highest on the planet. At 883 feet, the largest tower is taller than Rockefeller Center in New York. The two towers hold 224 cables with a combined length of 250 miles, 5 times longer than the Panama Canal. Engineers are now facing the most dangerous phase of the project, constructing the bridge deck.
It's a gorgeous view. Super deep.
New York-based architect Wendy Falk is at one of the project's highest points.
It's so difficult to even see to the bottom of this valley. It's impossible to build a scaffolding to reach up here, to build a bridge deck. So the engineers had to find another way.
Now, engineers need to support the nearly mile-long bridge deck while it's being built without scaffolding. A feat that might not be possible if it weren't for the innovators of the past. Engineer Luke Bisbee is at the Firth of Forth River, near Edinburgh in Scotland, to see a piece of engineering that could help out the team in China.
In the early 1800s, engineers were in a desperate race to build a rail line between London and Aberdeen along the shortest route. And this meant building a track along the east coast of Scotland. But this huge estuary, the Firth of Forth, was standing in the way and presented a major obstacle.
The typical method of building bridges at the time was to use temporary scaffolding to hold up the span while it was constructed. Once complete, the scaffolding was removed, leaving the finished bridge.
Here, it's completely impractical to build a bridge with a scaffold. Not only is the estuary very wide, but it's also very deep. And even if you could get your scaffolding poles down that far, the bottom is completely full of mud and silt, and so they wouldn't hold. Here, it would take an incredibly bold engineer to build the bridge, without a scaffold and of the enormous span lengths required, which had never been attempted before.
British engineer Benjamin Baker risked his reputation when he took on this impossible challenge.
I really can't believe I get to do this. Normally, only engineers who work here get to be here. Morning.
Morning.
Baker's solution is one of the most astonishing pieces of Victorian engineering anywhere in the world.
Now, this is just incredible.
This is the Forth Bridge.
Now that is a view.
A 1.5-mile-long cantilever design. The longest bridge in the world when it was built.
That is amazing. Engineer's bucket list, this one.
Constructing such a long bridge here was not going to be easy. However, Baker had an idea that might help the engineers at the Beipanjiang First Bridge.
Cantilever bridges are all about balance, with the weight of the steelwork on one side of the tower balanced out by the steelwork on the other. Baker also used that counterbalancing act to construct the bridge. The towers were constructed first, and then the bridge was built out symmetrically on either side. Every time a beam was added to one side of the bridge, an identical beam was added to the other side of the bridge. And in this way, the bridge became the scaffolding for its own construction, and it seemed to defy gravity.
It was an incredible solution, and Baker's risk paid off. The Forth Bridge opened in 1890. It now carries 200 trains a day and 3 million passengers a year.
130 years ago, Baker's ingenious balancing act changed the way that bridges are constructed. Engineers were no longer reliant on scaffolding beneath bridges during their construction.
At the Beipanjiang First Bridge in China, engineers have taken Baker's simple yet brilliant idea to jaw-dropping new heights. Like the Forth Bridge, they've constructed the deck without scaffolding by balancing it around the towers using cables.
In order to build a bridge without temporary scaffolding, let me show you what they did here. The approach span was already here, so in order to add a new section over the gap, I'm adding a cable to hold it up. To keep the forces balanced, I now need to add a cable on the other side of the tower.
Adding the cables symmetrically keeps the forces around the towers balanced and supports the deck.
And now I'm adding another section over the gap. And every time I do so, I have to add a cable to hold it up. And another one on the other side of the tower to keep it balanced. I add another section, I add another cable on the front, and I add another one in the back. And there you go, a perfectly built cable-stay bridge.
During construction, instead of building beam by beam over the deadly drop, the main span is built in sections. Then, for the first time ever, the deck sections are slid underneath the growing span. They're lifted into place. Then fixed to the end of the deck. Construction was twice as fast as traditional beam-by-beam building. After only 42 months, the two sides of this vast valley were finally connected.
Seems like I'm walking forever on this bridge. Can't believe how long this bridge is. What an amazing piece of engineering.
But before traffic could cross the massive main span, the team of engineers had one last problem to solve. After 42 months of construction, the Beipanjiang First Bridge finally connected the two sides of the massive Guangzhou Valley. Now, engineers needed to ensure the bridge was safe enough for traffic to cross.
There are so many heavy trucks in this region. When we design our bridge, we need to consider the loadings of heavy truck. The stiffness is very important for the bridge safety, especially for such long span bridge.
When heavy vehicles cross the bridge, if it's not stiff enough, the deck could sag. If this happens repeatedly, it will cause fatigue, which makes the metal very brittle, risking a sudden collapse. Stopping this huge deck from flexing is a serious challenge. The solution? An orthotropic deck.
Let me show you how the orthotropic deck works. We select two pieces of flat cut, and we make a bridge here, and then we put some weight on it. Wow, straight away, collapse.
The card isn't stiff enough.
So next, I will make an orthotropic deck.
The two pieces of card are still used, but this time the bottom one will be shaped differently.
I'm folding the card into box shape. It's just like the U-beam of the orthotropic deck. We can see what happened of the stiffness. A new bridge here, and we put the same weight on it. Oh, still working. Excellent. Just by changing the shape of one of these card, we can make it much stiffer.
Now that the bridge is stiffer, it doesn't flex when it takes heavy loads,
Still working.
solving the problem of fatigue. The orthotropic deck was installed in 34-ton sections. The finished span is so stiff it hardly flexes, even in the middle. To see it, Liu Ba is taking his colleagues to an area off-limits to the public, inside the bridge deck itself.
Wow, look at this.
Huh?
Yeah, very amazing.
Yeah. We can see the orthotropic deck above, including the top plate and the U-ribs. We use small ribs so we can provide enough stiffness for the heavy trucks.
The orthotropic deck is the final piece of the puzzle for this world record-breaking bridge.
It's hard for me to imagine how they actually built this thing on this height. I think it's very incredible. It's very beautiful.
Just beautiful.
The Beipanjiang First Bridge is taking engineering to breathtaking new heights.
I can't imagine how this bridge could be built if it weren't for modern-day technology.
You know, we really conquer so many challenges
Yes.
from the very beginning stage. It's really impressive.
Spanning the mighty Guangzhou Valley, this astonishing bridge is engineering on a legendary scale. Almost a mile long, with two landmark towers reaching more than 2,400 feet above the river. It has 250 miles of steel cables to hold up a 22,000-ton deck. It's an epic structure, unlike any other. The Beipanjiang First Bridge is cutting-edge engineering on a staggering scale. Finally joining two regions that have been separated for centuries.
We're now doing the same journey again, but instead of 5 hours, we're only taking 1 hour to cross this region. This is an absolutely amazing bridge, just really elegant. The view here is breathtaking.
This bridge changed the local people's life. It is incredible engineering achievement.
By learning from the pioneers of the past and overcoming terrifying challenges,